Hello everyone, welcome to today's Quantum Spacetime seminar. We are very happy to have Suvrat Raju from ICTS who will tell us about observables at spatial infinity.
So thank you very much, Pushkal, and the other organizers for having me over. So I'm going to speak today about some work in progress, and as I was just saying, this is going to be a rather informal talk. And so before I start, I should acknowledge my collaborators, I think all of whom are in the audience. And of course, Pushkal. Okay, so the idea of the talk today is that I got really sick of giving slide talks in COVID, and this I was very much hoping would be a physical talk where I could make it to TIFR, but unfortunately for various reasons I didn't manage to make it, and so I decided to try and do the best approximation I could to a Blackboard talk anyway, and so I'll try and do this entirely on the Blackboard. I don't have any prepared slides. These seminars are famous for being liberal on time, so hopefully we'll be able to get through some amount of material by the end of the seminar. Before so as I said, as Pushkal said, the title of the talk is about observables at spatial infinity. Before I start my talk, I want to start with some motivation for why we are engaging in this exercise. So this is the motivation itself could be the subject of several talks, but I don't want to focus on it, but I just want to give it as a motivation for why it is, as you will see, that we are trying to touch our nose the wrong way down and trying to describe observables at spatial infinity. Okay, so the motivation for this talk is a general theme that we've been working on with various collaborators, including Alok, Siddharth, Pushkal, and many other collaborators at ICTS and elsewhere, which is that in a theory of gravity, there's a general principle which one can arrive at, without invoking additional assumptions, but just from just by thinking carefully about the structure of constraints in gravity, which is that if you think of some Cauchy slice, and this is the region near infinity, somewhere here, then in a theory of gravity, it is the case that if I tell you all observables at infinity, so if I tell you this for all observables a infinity at infinity, so this fixes the state psi unambiguously. Okay. This is a surprising statement, right? It's very different from the way things would work in quantum field theory. In quantum field theory, so this is a slice at a single slice of time, the circle I've drawn. It's meant to remind you of a Cauchy slice at one point of time. Of course, in quantum field theory, you might have thought that, you could put some excitation here, but the structure of constraints in gravity tells you that, you can't prepare a state of this kind without also altering things out at infinity. And so gravity localizes information very differently from the way ordinary field theories do.
Sorry to interrupt so early, Suvrat. A infinity is what? A complete set of observables at infinity?
At infinity, right. So let's define some algebra which we'll call A hat infinity, and then A infinity is some element of A hat infinity. So if I tell you these expectation values for all observables at infinity, that fixes the state completely.
I see.
At a single point of time. So, these are observables which are, you can think of them as being living in the complement of a large ball at a single instant of time. And so, of course, in a quantum field theory, this would be impossible because, you could act with a unitary in the bulk, the place I've drawn this, and that unitary would commute with all your observables A infinity. And therefore, you would never be able to distinguish psi and U bulk psi are indistinguishable in a quantum field theory.
And this may be not something you're going to talk about. So in case not, the argument that there is such a complete set of observables is something you've done earlier, or
the argument is you look at the set of observables at infinity. I'll describe some more, but roughly, these observables are the limit of quantum field theory observables at infinity, including also the constrained observables such as the ADM Hamiltonian, the super translation charges, and other such things. So they're basically the usual observables at infinity, because at infinity, you think the language of QFT is good, and so you take those observables at infinity. And so this algebra A infinity is something that we understand, although this talk is partly about making sense of this algebra.
Okay.
But in some examples in ADS, for instance, we understand this. You take the set of fields and you take them off to infinity, and that gives you some set of observables at infinity.
Yeah. Okay. No, ADS, I do understand it, and I guess you'll talk more about it during the talk, right?
So
Okay.
The object of this talk today is to make more sense of this algebra at infinity.
Okay. Thank you.
So one example where we understand this well, where we understand what this algebra at infinity is that we look at the set of massless particles, and this is Scri plus. And for the set of massless particles, it turns out that if you look at the algebra here, which is Scri plus minus, then the algebra in the brown region, which is the set of all observables for retarded time in minus infinity to minus 1 over epsilon for some value of epsilon, is sufficient to describe all observables on Scri plus in a theory of which has massless particles. Okay, so in a theory with massless particles, and this is something that we argued at length with Alok, Siddharth, and Pushkal a couple of years ago. Okay. The algebra is complete in that this algebra, an element of this algebra in this brown region can be used to approximate some element of an algebra here. This is a realization of the general principle I mentioned, because if you think of massless particles, then Scri plus is the limit of Cauchy slices, in that you take a Cauchy slice and you push it up towards infinity, and if you do that, you will get a Scri plus. There's a similar result at Scri minus, by the way, which is that all the information available on Scri minus is also available on Scri minus plus, which is the future boundary of past null infinity. So, this is a realization of the general principle I mentioned, which is that all the information available in the bulk of a Cauchy slice is also available near its boundary. And in this case, we can make it very precise. Okay. Now, I want to talk. Now, what is missing in what I said right now is what if you have a theory of gravity that is coupled to, so massless particles and of course, and gravity. Okay. So what if you have a theory of gravity that's coupled to both massless and massive particles? Now, and that's what's going to be the object of this talk, but just before I go there, let me just try and give you 5 minutes more on why this is something interesting, why this is something you should think about. First, this is something interesting because, it gives you a new way, and one should really take this seriously, of thinking about how information is localized in a theory of gravity. So, for instance, if one thinks about the information paradox, which I'm not going to talk about much, but in this talk, but if one thinks about the information paradox, one of the ideas of the information paradox is that, if you think of some black hole, then, and this is its horizon, of course, the horizon is not at infinity, but let me try and extract the moral from the story that I mentioned. And one thinks of the horizon, one of the ideas of the information paradox, which is the way Hawking phrased it, is that the horizon is information free, in that, classically in general relativity, there's a no-hair theorem that tells you that regardless of what fell in, the horizon is just settles down to something that's determined by a few global charges. And moreover, in quantum field theory, there is something called a split property that tells you that, you can prepare a state with some excitations here, which are independent of the excitations outside the horizon. So in QFT, we have a split property. And really, this was the argument for, that Hawking provided for information loss, which is you take a Cauchy slice. On that Cauchy slice, the interior of the black hole and the exterior are two parts which are space-like separated. And the split property tells us, that we can prepare the state in the interior independent of the exterior. And therefore, an observer outside should trace over all degrees of freedom in the interior, because that observer is space-like separated from them, and therefore the observer outside will see a thermal state. So Hawking's paradox was, this was really how he framed it. It wasn't in terms of the fact that the radiation is thermal, because radiation from a pure state can also look very close to thermal, but it was rather this fact that you look at the interior and the exterior, they're space-like separated, and therefore the observer outside has to trace over the interior. But if this assumption is not true in gravity, and you can show even in perturbation theory and using the more precise arguments I mentioned earlier, that the no-head theorem doesn't hold and the split property fails, then that gives you a precise sense in which the Hawking argument was erroneous. So, people say, where is the error in Hawking's argument? And this tells you where the error in Hawking's argument is. It is in the assumption that gravity localizes information the way ordinary field theories do. So that is one interesting, one reason why it's interesting to think about these ideas. The second reason it's interesting to think about these ideas is, so this is one motivation, is that it tells you why gravitational theories are holographic. Why is it that gravitational theories are holographic and non-gravitational theories are not? So in particular, even in ADS, we can extend the arguments that I mentioned previously, and we did also in this paper with Alok, Siddharth, and Pushkal. And we can show that if you look at ADS, that all the information in the bulk of ADS is available in a small time band here, which is much smaller than the light crossing time. And that tells you, okay, that's not quite, that's a little weaker than the statement of ADS-CFT, which tells you all the information is available in a time slice, but it gives you a strong indicator for why it is that, in gravity, the information is available all the way near the boundary. So in the bulk, you would say that, this is the statement that all the information is available in the region here. And that gives you, just starting from gravity, a reason to expect that gravitational theories should be holographic. So, of course, in ADS, we understand this independently from ADS-CFT. And so the question, we'd like to ask is how this works in flat space. And in flat space, the result I mentioned earlier about all information at null infinity being available also near its past boundary gives you an indicator for where we should look for the holographic dual of flat space. And today I'm going to speak a little bit more about that, which is about, how one can include massive particles in that story.
Sorry, Suvrat, can I interrupt you?
Yes, of course. Yeah. Yes.
Just to go back to your previous slide, and I know you and Pushkal and Siddharth have told us a lot about this in others, but let me ask the question to you in a very dumb way, because I don't even understand algebras and so on. All I understand is detectors. Is the statement that a bunch of detectors which are detecting the outgoing radiation, quote unquote, between minus infinity and minus 1 upon epsilon, will by measurement be able to tell you everything about what happens along Scri plus? Is that the statement?
Yes, that is the statement. But remember, they also have to measure the ADM Hamilton. And let me give you a simple example. So let's say we had a shock wave of this kind that was coming and hitting Scri plus at a later time.
Okay.
So this shock wave I can model as, say, there's a news operator on Scri plus. Let me model it in this way, acting on the vacuum. This is the news operator integrated over retarded time, f of u. With some smear. So this is the profile of the shock wave, f of u. And n is the news operator. So this is the action of a unitary. I've made it perturbative. I've added a perturbative parameter lambda. But this is a shock. If f of u is centered here, so I can make f of u have compact support. And this is a shock wave that's coming and hitting null infinity here.
Yeah.
And now in a quantum field theory, this unitary operator commutes with all observables in this Brown region, and therefore it's completely undetectable. However, the point is that, if you measure now in this particular example, let me take this state psi. If you measure psi, if you measure psi and you measure the limit of the Bondi mass as u goes to minus infinity, and also another, so let me call this m of minus infinity. So let's say you measure this, and let me since I'm allowed to work perturbatively, let me do this. So let me just, then you can show that this object, so this insertion of u naught that you see here is in the region minus infinity to minus 1 over epsilon. You can check that this turns out to be f of u divided by u minus u naught. I forget the exact power. It's maybe. Okay. And this is integrated over u. Okay? But you see that even though f of u doesn't have support near u naught, this function does have support over u naught. And what is more, if you know this function for a range of u naught in the range minus infinity to minus 1 over epsilon, you can extract f of u completely, because you can get all the moments of f of u. Now, you shouldn't be so surprised about this. The reason this is happening physically is because, in a theory of gravity, all the information comes from infinity. So it's not that the information is jumping out. Even classically, you see, you would not have been surprised if I told you I would know the mass of the shock wave in the bulb. Right? If I just told you I know the mass, you would say, sure, from Gauss's law, you know the mass. And the reason you know the mass at scribe plus minus out at infinity is because, the information eventually had come from infinity. So there's a Gauss constraint that tells you the mass. But classically, you know only the mass. But, in quantum mechanics, apart from the Gauss law, there's also the uncertainty principle, which tells you that, if you have something of definite energy, then that thing of definite energy is also delocalized. And therefore, it can't both have definite energy and be confined to a compact region. So once you measure the mass, if you also measure correlators of the mass with other dynamical observables of the kind that I'm doing here, that is sufficient to completely identify the state. And it's a combination of these two physical principles. I mean, I can give you a more formal proof, but the physical principles being the Gauss law and the uncertainty principle. And so, in the quantum theory, you get more information at infinity than you do in the classical theory. And it's not because information is jumping out, it's because the information came from infinity, just like, the Gauss law is not some violation of causality. It's the fact that the information came from infinity, and so it's always there at infinity. It doesn't, it never goes in completely. You can't erase the traces of information at infinity.
I see. Okay, no, thanks. And you should go on. But just to ask one last thing,
Yes.
I mean, is it that the information is in some soft mode so that if you actually try to measure in the very narrow, quote unquote, very narrow time band you have drawn in Brown, you won't be able to measure it? Is there a conflict like that because of the uncertainty principle? I mean, yeah, go ahead.
Yeah, that's a good point. If you invoked an energy time uncertainty principle, you might have said that this energy that I'm measuring here, you can't measure. Now, first of all, let me say two things. First of all, this, even though it's small in the Penrose diagram, this is actually a semi-infinite interval.
Yeah.
Okay, so that's one thing. But the second thing is that you might still have said that there's an energy time uncertainty that prevents me from being able to measure this. But energy time uncertainty is not something that's manifest in quantum mechanics. The way you should think of this is that you have a patch of flat space and you have observers outside. And if you do have observers outside who have access to an external clock, then it's possible for them to measure the energy of a system in an arbitrarily short amount of time. So if you use the usual rules of quantum mechanics, which is that there are observers who are external to this patch of flat space who have access to an external clock, then nothing prevents them from measuring the energy as fast as they like. Now there's some literature in this by Aronov and Bohm and then by Aronov and Resnick, which talks about what if you have an observer who is inside the system. That the observers don't have access to a clock that's external to this patch, but what if they're inside the system? And then it gets into a pretty confusing setup, where you've to ask, okay, well, how does quantum mechanics work if the observer is not external to the system?
Okay. No, but here we can localize it inside. I agree. I see. Okay. Go ahead. Thank you.
Okay, fine. So that's the motivation. But what is missing in the story that I mentioned is that this story works with the news operator, which is an excitation of a graviton. Sorry, is there another question?
Yeah, can I ask one question?
Sure. Yes.
So if you have some charge distribution, you would do a similar thing with charge operator in electric field?
No. Because the reason is, there's no uncertainty principle for charge. There's nothing that tells you that something of, what was important here is there's an uncertainty principle for energy. So in particular, if you had a charge distribution and I acted with the operator e to the I, just if I replace this with trace of f squared, then you see this really in a gauge theory commutes again with everything inside, because there are local gauge invariant operators in a theory of, in a gauge theory. So the fact that there are, and this is the one I wrote here, if I erase this n of u and I replaced it with trace of f squared, then, this operator in a gauge theory in the absence of gravity would commute with everything in that Brown region. And the reason is there's no uncertainty principle for charge. There's nothing that tells you a definite charge has to spread out, and there's positive and negative charge. I can combine them to do something which would make it impossible for the observer at infinity. So no such principle exists in gauge theories, but it does exist in gravity.
No, but in gravitational theories with the gauge theory?
Yeah, so if you have gravitational theories and the gauge theory, you see this operator would still have a mass. So for this, I would have to measure something which looks like trace of f squared. So I'd insert another gauge invariant. Trace of f squared is gauge invariant from the point of view of the gauge symmetry. It's not, there's no such thing as a local gauge invariant operator in gravity. There is such a thing as a local gauge invariant operator. Yeah.
How would you distinguish charges, electron versus positron?
Oh.
They have the same mass.
Because so you would have to, so you could ask an even more refined question, which is you could ask, how would you distinguish states with a global symmetry? You don't even need charges.
Okay.
So okay, this is the talk, different talk, but okay, let's try. So let's say I gave you two states, f of u 0, okay, and I gave you a state which looked like where phi 1 and phi 2 are fields which are related by global symmetry.
Yeah.
Okay. Notice I was not measuring only the mass. It's very important that, we don't do this only by measuring the mass or the energy. We look at correlators of the energy with other observables. So you measure the mass, that projects you onto some energy eigenstate. Then you look at correlators. In this particular case, you will find that psi 1, let me write, this is the Bondi mass at minus infinity. Phi 1 of u naught is not equal to 0. And in fact, it's the old answer that I wrote previously. But psi 1 with h of phi 2 at u naught is psi 1 is equal to 0. You see, so I break the symmetry by my insertion of the second operator at infinity. I'm allowed to insert this operator as well. So even though the states are related by a global symmetry, I can measure two different correlators. One of them is the correlator of the energy with phi 1. The other is the correlator of the energy with phi 2.
Okay.
And in state 1, one of them, and conversely in state 2, h phi 2 would not be 0 and h phi 1 would be 0.
Okay, thank you.
Okay, thank you. And same for electron, positron. Okay. Okay, thank you. Very good. So that's good with the motivation. Let's go on to the bulk of the talk. Okay, good. So now, what is missing in all of this? All of this works very nicely if you have massless particles, because you describe massless particles at null infinity, and then, you can say you get the information at the pass boundary of null infinity by measuring correlators of the kind that I discussed. Now, what about massive particles? Okay. So the convention, massive particles are very hard to describe at null infinity, in that there is no good limit of massive particles that goes out to null infinity. Conventionally, when one talks about the S matrix for massive particles, what we do is something slightly different. What we do is we take the limit to past or future time like infinity, which is we go to I plus or I minus. Okay? And massive particles are things, where the world line starts at I minus and goes out to I plus. And this is a perfectly acceptable description of massive particles. It's what we use for the QFT S matrix. But it doesn't fit within the meta-narrative I was trying to give you, which is that, all the information in the bulk is available at the boundary, because, I plus and I minus are not the boundary of the Cauchy slice in any sense. Now, so what I'm going to try and do is try and give you a description of massive particles at a blow up of spatial infinity. Okay? And the reason, as I said, for doing this unusual procedure, as I said, I touching my nose this way, is that we want a notion in which holography should work with massive particles, and working in I plus or I minus does not seem natural from the point of view of holography, where we want to say in gravitational theories the information is out at infinity. So that's the reason for the talk today. Now I should say that the proposal I'm going to describe is subtle, and we've not worked out all subtleties, and maybe in the end what we're trying to do doesn't work, and we have to fall back in some way on the description at I plus and I minus. But it seems to us that it's a very interesting thing to explore, whether there's an alternative way of understanding massive particles at infinity, but not at time like infinity, at spatial infinity. Okay, so that is the idea. Okay, so I'm going to divide my talk into two parts. The first is a purely QFT part. Okay, so part one, and this is a QFT, no gravity. In fact, for most of the talk, I'll be in free field theory. Okay? So this is part one, where I'm going to try and describe that if you have phi bulk, massive field. This leads to a set of observables at I naught. And this is going to be part one of my talk, is going to be to describe this map between bulk massive fields and observables at a blow up of spatial infinity. I'll explain what that means in a minute. Okay? This is, as I said, a QFT thing. So, even if you don't care about holography or gravity, or you think you don't believe anything I'm saying about gravity, this is something which is of independent interest. Okay, maybe it's wrong in some deep sense, but we think it's something that's of independent interest and certainly worth exploring. Okay, so that's going to be part one. And then part two is we'll argue that all bulk information is available in a subalgebra in I naught and I plus minus, and I'll explain what that result is a little bit more precisely. It's actually in a subalgebra of I naught, of observables at I naught and I plus minus, which I said earlier. So part two is about gravity and part one is not about gravity. So part one is just a QFT exercise, which is what I'm going to do for the next panel.
Yeah. Suvrat, one quick question for you. In the Scri plus case, does your argument also say that you can do things sitting at Scri plus and Scri minus maybe that will create something space-like separated away instead?
Yeah, the argument does say that it gives you operators and therefore, you can do something at Scri plus. That doesn't work. I don't know if you're there for the earlier part. So, these simple correlators I was measuring are not of that kind. But in principle, if you act with a suitably complicated operator, then indeed you can do things that will create some excitation inside. And I think the way to understand that is, if you do something suitably complicated, then your notion of bulk locality, just completely breaks down. And that's how you reach into the bulk and insert something. But for these simple perturbative arguments that I mentioned earlier, you don't need to do that. You can understand them simply.
Right. And do you have a sense of how is there a way of saying how complicated that thing? Can you create
So I guess this is what we were discussing also the other day. So I can write down what these observables. So these observables involve in the way we think of them as some projector on the vacuum, and that's something which So we try to make some estimates for how complicated it would have to be if you wanted to create this thing in the inside accurately enough. And okay, so some estimates are that in ADS, for instance, the complexity goes like log of n. You'd need to act with some polynomial of order log of n in order to create this. But as I said earlier, also we don't have a very good answer to that question. One answer to this question, as I said, is this log of n comes from the following estimate. The key complicated operator we need is P0. And this you can think of as e to the minus alpha h, where limit as alpha tends to infinity, e to the minus alpha h. And, you might want to keep, alpha to be of some large order. And if you do that, you would have to keep n orders in the polynomial of h at infinity. And that's why it would become very complicated. If you don't want to take the limit formally going all the way out to infinity, but you want to keep alpha to be large enough that you can distinguish,
Yeah. This estimate doesn't seem very complicated. It's not e to the power n squared, for instance.
It's not e to the power n squared, but in terms of polynomials, you never need to act with a polynomial of order e to the power n squared. An n-point polynomial is already very complicated, right? That n-point polynomial is, so usually in terms of, if you count complexity in terms of what is the size of the operator, that doesn't scale exponentially. That usually scales with some power of n.
I see. So I'd stop this, but you could, in principle, set up define a protocol to do this. Could we set up an experiment that will actually, set up a ring around the Earth and then create something in Bombay?
The other kind of experiment might be something which we really try to explore using a protocol, which is you try to measure the energy and determine the probability, which is you do a measurement. Right. And that would already be interesting enough in that, you take a small tabletop and make some measurement around it and try and determine what's happening inside. This thing is much more complicated.
Yeah, I was just wondering whether it would be worth setting up a thought experiment for what you would actually have to do it. And that will give us a sense of how complicated it is.
Yeah.
Anyway, we can talk about this later. Sorry for this.
Yeah, roughly it's a question of how complicated is it to act with an endpoint polynomial in AD. So, if you have some scale, you divide that with the Planck. So let's say you have some experiment over size L, you divide that with Planck scale, that gives you some notion of N. And then you want to ask, how complicated is it to act with an endpoint operator in that? So, in the end, when you act with it, you have to turn on a source dual to this endpoint operator if you really wanted to act with it.
Right.
So that's so the operator itself is complicated, but now you want to add it to the Hamiltonian somehow.
Right. I was wondering whether we could set up a physical protocol, what we would actually need to do. That anyway.
Yeah. The thing is, okay, we could discuss this more, but if you ask something much simpler, what do you need to do to measure a 2-point Whiteman correlator or 3-point Whiteman correlator? That's already something for which physical protocols are not so easy to get. Usually we say, we'll just add the operator to the Hamiltonian. But what does it mean to add the operator to the Hamiltonian if you have a 2-point or even a 3-point correlator? So this is something I thought about a little bit about the physical protocol, and I found that there were questions which, even of this kind, which I don't know the answer to. We could talk more about it. But
okay, great.
I don't have something much more precise to say about a physical protocol for creating.
Yeah, I feel that a physical protocol, if we can, will actually give us a sense of how complicated it is. Because some formal notion of complexity is something, but if it's something we could actually imagine doing. Yeah. Okay.
I agree. Yeah, it would be interesting.
Okay. Yeah.
Okay. Okay, fine. So in any case, for some time, let me put aside all questions about gravity and just say something about. This is part 1 of the talk, which is just about QFT. Okay. Okay, good. So let me so I'm going to start by just describing first free fields in Minkowski space. So we'll just consider some free massive field. Okay. Now, before I say something about the field, let me just tell you something about the geometry. Okay, so the metric of Minkowski space, of course, is this. And when we talk about the blow up of spatial infinity, so let me first introduce just geometrically what that means. Okay, so what you do is you introduce some coordinates that say which are good outside the light cone. So if you're on the light cone, these coordinates are good in this patch. In this patch that you have here, and then this coordinate is good for this patch, and in fact you can if you draw a Penrose diagram in higher dimensions, in these slices of constant rho roughly do the following. So this is the light cone, and these are slices of constant rho. So rho is light cone distance, which is positive here. Okay. Now, in these coordinates, the metric takes the form so I'm restricting myself to 4-dimensional space. We could work in other dimensions, but for now, let's just think about 4 dimensions. And this is the metric of DS3. Okay, so this is a 3-dimensional de Sitter plane. And we have a copy of this DS3 at every value of rho. Now, when we talk about the blow up of infinity, of spatial infinity, is just obtained by taking rho tends to infinity. Okay. So it's the slice that roughly does this. Okay, it's the second slice that I do.
Sorry, so Suvrat, your coordinate system breaks the translational invariance of space and chooses one point as spatial, right?
Yes, that is correct.
Okay,
that is correct. But if you take rho goes to infinity, it doesn't matter which point you chose. I mean, if you move around by a finite amount, you'd be at rho equal to infinity. So
no, but even when I take rho goes to infinity, it's hitting Scribe+ at a particular point. Right?
It's hitting Scribe+ at a particular point. That's true. But notice in this rho goes to infinity point, if I'm at some finite value of tau and omega, I will always be in a blow up of spatial infinity, which is I'll be very close to this region. So the fact that the slice goes here and here doesn't really matter. But you're right, and you're right. One should keep track of that subtlety, and it'll become apparent also a little bit later. But if you take rho goes to infinity and you're sitting at a finite value of tau and omega, that really literally gives you a blow up of this point, which in the Penrose diagram is a singular point. then it doesn't matter. But you're right that, if you go to rho goes to infinity and you also scale tau in a way that's large, then indeed, this becomes important. Okay.
Just show the previous slide again once, the coordinate transformation, just so I make sure. Okay, thank you.
Okay. So very good. So now there's a convenient parametrization on de Sitter space, which is actually the standard parametrization, which is you take the Minkowski coordinates and you divide it by rho, and of course these coordinates obey x mu is equal to 1. Okay. So we'll sometimes use these capital X coordinates. My handwriting is so bad that I'm sure you can't make out capital X and small x, but usually if I write X, I mean capital X. Okay. So capital X is just, this is a slightly redundant parametrization of points in this de Sitter space, but it's convenient to use sometimes. Okay. Okay. So now let me say something about field theory. So
Pushkal, can you hear me?
Yes.
Yeah, we can hear you.
So what happened? You couldn't hear me? Say, Pushkal, you can't hear me?
I can hear you. Shiraz, did you have a question?
I think the
Okay, great. Okay, so where was I? So I had just introduced this blow up of spatial infinity, which was just that it's true, you pick some origin, but then you introduce this coordinate system, and if you take rho goes to infinity, that gives you a blow up of spatial infinity. I mean, this is a useful concept because a spatial infinity is a discontinuous point in the usual Penrose diagram. I mean, for those of you who've been following, this story about Andy's story about celestial amplitudes and so on, you will see one of the things that's emphasized often in that is that the future of Scry minus is different from the past of Scry plus, and you have to do some antipodal matching and so on across that, but these two are not the same thing. This part of the Penrose diagram is not the same as this part of the Penrose diagram. And what this blow up of spatial infinity, which was introduced by Ashtekar and Hansen and others, does is it gives you a smooth interpolation between Scry minus to Scry plus. Okay? So it gives you some way of interpolating between those two. There are similarly blow ups of time-like infinity as well, which Alok and Miguel and so on used very effectively in understanding massive particles and the S matrix. Okay, so this is the utility of this blow up of spatial infinity, which is something that's been discussed in the GR literature, basically to try and smoothen out this singular point in the Penrose diagram. Okay, great. So so this was the geometry of the blow up, which, as I said, gives you a copy of de Sitter 3. And now what we want to do is we want to consider some massive field. Let's start with a free field propagating in space. So let's just consider some field that obeys some equation of motion. Okay. Now, a convenient basis to expand this field is, by the way, if there are questions about this part or about the last part, please feel free to stop me. So if we look at solutions of this equation of motion, then one convenient basis, which is tuned to this coordinate system that we're using, is to expand it this way. Where this guy is what's called the Macdonald function, or is the modified Bessel function of imaginary order, and this integral goes from 0 to infinity. And this object here, phi nu, is something that obeys an equation of motion in de Sitter. It looks like a massive field in de Sitter, in that it obeys not the Minkowski box, but the de Sitter box. It obeys this equation. Okay. So this is a set of solutions to the equation, just to the Klein-Gordon equation. Okay. And so this allows you to break up a field in Minkowski space, a massive field in Minkowski space, into an infinite set of massive fields in de Sitter space, which are these phi nus, and the mass parameter, which is nu in de Sitter, ranges over 0 to infinity. Okay. Now, we can also expand this phi nu in some basis, and this is just elementary Minkowski space quantization. So if one convenient basis to expand phi nu is to write phi nu as there are other bases as well, but here is one basis. And these are some annihilation operators. These are some modes, which I'll write down in a minute. Okay. And these are the standard spherical harmonics. Okay. These modes are canonically normalized. This normalization factor, it goes like e to the pi nu by 2 at large nu, which will be relevant in a minute. And these modes are some modes. The details are not so important, but let me just write them down for completeness. Okay. So they look like some hypergeometrics. Let me see if I can get it all right. 1 plus I nu minus e to the minus 2 tau plus c nu L into e to the I nu tau into another hypergeometric. So these details are not important, as I said. The only thing to note is that these modes look a lot like Fourier transforms. You might have thought, there's some hypergeometric, but in fact, this hypergeometric has some negative number sitting in its, in its second argument. And for those of you who've played around with these hypergeometrics, this actually makes the hypergeometric some finite polynomial. So it's some finite polynomial in e to the 2 tau of order L. This L is related to the spherical harmonic here. So it's basically a mode which looks like e to the minus I nu tau plus some constant which I won't write down. It's some ratio of gamma functions times something else which looks like e to the I nu tau. Okay, so that's how you should think of these modes. So they're effectively, they're effectively Fourier modes, although they're not quite, because they have these hypergeometrics that are sitting there. Okay?
So Suvrat, your de Sitter is global de Sitter, right?
Yes.
And I thought that modes in de Sitter, when they reach plus or minus infinity, sort of freeze out.
When they reach plus or minus infinity, they sort of freeze out. So these modes are what are called Euclidean modes in de Sitter, which are, let's see. So you mean, you're asking why is there then e to the minus I nu tau at all?
Yeah, I thought they oscillate in the middle, but they sort of freeze out when they go to large tau. Right? That's why we have CMB. Right?
That's indeed true, but you're asking why is there e to the minus I nu tau? How is that consistent with the fact that...
It's a very stupid question, I know. Sorry.
No, there could be, but usually there is some, as Shiraz says, there is that mass-dependent tau, but the hypergeometric has, also some oscillatory thing, and finally it does go to it.
No, I think this e to the I nu tau will persist because there's this hypergeometric, the leading term is 1. And so there's something which goes off. I mean, this will just go to 1. So you're asking why is it consistent? You're right. That's a good point. Sorry, I should have.
Is it a positive mass? It is a positive mass, right?
Yeah. This is a positive mass.
Then it's strange.
This is a positive mass field in de Sitter. Sorry. There is of course. This term which sits in front. I don't know if that is enough to. So this term indeed does die off. So it always gives you a 1 over cos tau.
Only the massless guys will die out, will freeze, Shiraz.
You mean the ones with nu equal to 0?
I see. You say the massless guys freeze and the others
will have some oscillation which looks like e to the I.
Yeah, I think only the mass. It's like in ADS, asymptotically, only the mass determines the fall off.
Thank you. Yeah,
Here, the mass will determine the oscillation.
Yeah. Thank you. Indeed, that's correct. Thank you. So indeed, asymptotically, these things will look like, apart from a normalization factor, so they die off in magnitude, but then you're saying that there's an e to the I nu tau, and so that is determined by the mass, and it looks like, okay, thank you. Yeah, thank you.
I just one more about this. I mean, in the middle, how fast it oscillates should depend on its L.
How fast it oscillates should depend on the L. Sorry, why should it depend on the L?
Because you've got excitations in space, and that gives you fast excitations in time, right? It's just like flat space. Whereas once you go to infinity, as Sandeep was saying, the tau behavior depends not on the spatial behavior. It's just on the mass. I can't see that in this formula. Sorry.
It's true that in the middle, this part is important. It does depend on L. Whereas, if you go asymptotically, you get only something that depends on e to the minus I nu tau. You're asking, if you do a Fourier transform, why is it that there's a relationship between
That's what I was asking, but maybe it will just come out when you look at this.
yeah, I don't have I should have a clearer answer to why this happens. But I mean, there is clearly some dependence on L, which is important at near tau equal to 0, because this is something at -1, and so the hypergeometric has some important role. But I can't immediately see how.
Okay. Thank you.
Yeah. Okay, I should have a clear answer, but I don't have one right now.
Okay. Suvrat, just one quick question. Yeah. What picks out this particular linear combination of the two modes?
So this particular linear combination is, I mean, in Minkowski space is just forced on you because you take, the plane wave modes. But this is also a nice linear combination in that these linear combinations are what are called the Euclidean modes in de Sitter. So they are the ones that correspond to, the Hartle-Hawking state. In de Sitter, there's all this discussion about, they're the ones, if you continue tau to imaginary tau, so that de Sitter becomes a sphere, and they are the ones which are regular at the south pole or the north.
I see. Okay, thank you.
These are the ones which when you take tau equal to minus I pi by 2, I might be saying it the opposite way.
No, I understand.
And the conjugates are regular at the other pole when you continue.
Perfect. Thank you.
So that's a nice feature. Of course, we don't have any choice here because we are quantizing a field in Minkowski space. So, we know how to quantize that, and there's a vacuum. But it so happens that these modes in de Sitter are also nice from the de Sitter point of view, in that they are the natural modes that one uses to quantize global de Sitter if one takes the Hartle-Hawking state as a vacuum, the Euclidean vacuum.
You have not specified what CRL is, right?
What C nu L is?
CRL.
I have not specified it. It's some ratio of gamma functions. I could, if you want, I can write it down.
No, it's fine. For some particular.
Yeah, it's some constant. I haven't written it. Yes, it's what ensures the right linear combination that these things are regular at tau equals I pi by 2.
Suvrat, I'm confused about one small thing, if I may ask, which is basically you've constructed a bunch of Rindler observers, right? You've divided that Minkowski wedge into two halves, and these are a family of Rindler observers, right? Each of which sees this de Sitter 3. Isn't that right?
Spherical Rindler. It's not two halves because, these guys go around.
Okay, these guys go around.
There's a sphere. So they go around. I mean, I've suppressed it here, but they go around the sphere. But you're right. It's a little bit like some spherical Rindler observer.
I see. Right. But now what I wanted to ask was, when you're dividing the modes into positive and negative frequencies, etc., I mean, the Minkowski vacuum and the Rindler vacuum are, of course, different, right? And here, what you want to, I mean, what I guess you do your quantization just like you would do for Rindler, but then your vacuum will be something complicated.
No, the vacuum here is so that's what I said. So if you look at the state, which is, this is the Minkowski vacuum. This is annihilated by the modes I wrote down.
Yeah, that's what you said, but I was a bit confused because if it were Rindler, then that wouldn't happen.
I mean, I could always choose the right set of modes, right? I could have said, if you use Rindler, first of all, it's not quite Rindler because, you have a Cauchy slice, so it's not half. It's not like I'm using the static patch of de Sitter. So I'm going around, so it's a Cauchy slice. Of course, I could take Minkowski space and I could go down in a Cauchy slice and use some other modes so that I see the global vacuum, provided I use the right kind of modes.
I see. Okay.
I mean, it's not that I see only half of the space, right? These modes see the full space because they see the full Cauchy slice.
Yeah. Okay.
Yeah, and also the modes you're looking at have e to the power I tau and e to the power minus I tau.
Yes, they have e to the I tau and e to the minus I tau. So they're not only like positive in de Sitter time, but they are natural in de Sitter from this other point of view, and that they come naturally from a Euclidean continuation. But it's true, they're not just e to the I tau or e to the minus I tau in de Sitter time.
But how to see that the Euclidean modes are the same as these ones?
It is true that they are the same as these ones. This expression you just get by solving the field in Minkowski space. So let's say you just do Minkowski quantization and ask what are the modes which are positive frequency. You will land up on this. You just solve the Klein-Gordon equation. You ask what are the modes. It so happens that these are also Euclidean modes in that, if you continue tau to I pi by 2, they are regular. So it's a nice feature that if you look at positive frequency in Minkowski space, that also corresponds to Euclidean modes in de Sitter space. I don't know of a quick argument that would tell you it had to happen, but it does happen. It's a nice feature of the quantization.
Usually, yeah, okay. I just show that 2f1 in terms of the positive and negative frequencies once more. Sorry.
Here, it's on the board. Can't you? Is it not for you?
Oh, okay, okay. Sorry, I see. Okay, I see. So as you say, it's both, as Shiraz was saying. Okay, I see. Okay, go ahead. Thank you.
Okay, fine. So now the point is that if you, in terms of this expansion that I had, which was in fact this expansion, there's a natural sense in which
Sorry. Abhiram, please mute yourself.
So Abhiram, I'm not able to hear. Is there a question or? So was there a question or?
No, I don't think so.
Oh, I see. Okay, fine. So okay, so if you look at this expression, then you see in this expression there is a natural sense in which you can take a limit as rho tends to infinity, and let me just copy this expression. And the way that works is, we notice that this object ki nu of m rho has, takes the form e to the at large rho. And large, of course, means large compared to m. So, e to the m rho is the dimensionless number, which must become large. And when that happens, this has this asymptotic limit. And this suggests that, we should define the following extrapolate dictionary, which is z of x is limit as rho tends to infinity, d of rho times phi of rho x, where this d of rho is the factor of rho that was sitting up front. There was another factor of rho, that's this factor of rho, and then this factor of root of m rho and e to the m rho. Okay? So it suggests this extrapolate dictionary and suggests that this set of observables is a good boundary limit of the bulk massive field. Okay? So this is our base. I'll say some things about subtleties of this proposal, but this is the basic proposal we have for what are the right observables to look at in spatial infinity. So just like in ADS we say that you should look at the coefficient of some r to the delta. We say that in flat space you look at these exponential tails of massive fields, and that gives you some set of nice observables at spatial infinity, which are these observables which I'm calling z of x.
So sorry, Suvrat, I missed this. So the idea is you just strip off all this row dependence from the Ks,
yes,
and then you are left with whatever x dependence.
The idea is that in this coordinate system there is a natural sense in which you can take a rho goes to infinity limit. If this limit, for instance, depended on nu, as would happen if you were to try to go to null infinity, then it wouldn't make sense to take the idea is that in this basis there is a natural sense in which all the modes have the same decay at large rho. And that's why you can strip it off to get something meaningful.
Suvrat?
Yes.
So just one comment. This Euclidean mode is equal to this positive energy modes in Minkowski space. I guess one could understand that by seeing that if you attach hemispheres,
yes,
these Hartle-Hawking type hemispheres for all the de Sitter slices,
yes,
then effectively you are working in you're gluing a Euclidean space.
Yes.
At t equal to 0 in Minkowski space. And if you insist that you have regular solutions there, that means you have some decaying solutions which would pick out some positive energy solutions in Minkowski.
Yes, that might work. So you could take Minkowski space and you could do a continuation to Euclidean space, not using continuing standard Minkowski time, but by continuing the de Sitter time, by continuing these de Sitter slices. And then you could try and continue back in this way, and that would give you that's one way to understand this. Indeed, yes, that's one way to understand this. That's what you're saying. Right? You continue Minkowski to Euclidean by continuing the de Sitter time.
Yeah.
Sorry, one quick question, Suvrat. Instead of taking constant row slices and going to rho equals and rho to infinity, if you do like a funny shape, multiply rho by some function and then send that to infinity. Is there something simple one can say about the operators one gets? So, for example, in ADS, that would give a while transformation of the CFT correlators.
Yeah.
Something simple that you can say here.
Something simple that if you tried to translate rho, for instance, you would get something of that kind. But if you try to rescale rho, like you took some other function, so it's not as nice as the CFT operators, in that there isn't this conformal symmetry as far as it's true that if you try to do a translation, that's something that would act nicely, in that it would rescale things on the boundary. But you're right that in ADS, you say you look at the metric and it has some pole. You take whatever coordinate, and it doesn't quite matter, right, what coordinate you choose that has a
correct.
And that's because the boundary has this conformal symmetry. I'm not sure what the analog of that here is.
Okay, thank you.
By the way, Pushkal and Siddharth and Alok, you're on this call. So if you have some answer to these questions that's better than the answer I give, please feel free to jump in.
Sorry. Yeah, it's just a sort of similar question. This e to the power m rho seems like it's tuned so that your source will have a finite effect at the origin.
Is source it'll have a finite effect at the origin. Okay.
Right, because e to the power minus m rho is the decay.
Yes.
Rho is the proper distance, right?
Yes.
Okay, so if you turn on a finite source, its effect at the origin would be of order e to the power minus m rho.
You mean at infinity?
If you turned on at your boundary a finite source,
then it would have some effect of size e to the minus m rho. Alternately, if you turn on a finite source in the origin, it would have an effect of size e to the minus m rho at infinity.
Right, but I'm trying to understand, since you're doing these boundary operators, I'm trying to see, if I hit the boundary, what effect it has where.
Yes.
Okay, so it would have an effect of e to the power minus m rho at the origin. Therefore, if you multiply it by e to the power plus m rho, it will have a finite effect at the origin.
Okay, sounds right. Okay.
Now, this worries me because the origin is sort of being singled out.
Yes.
There are other places in the bulk where it would have an infinite effect.
Nowhere where it would have an infinite effect. You mean it would have a larger and larger effect as you go inside?
Well, if I go sort of halfway to the origin.
That's still infinitely far away from the origin though, right?
No, halfway in rho.
Isn't that still infinitely far away? Because rho is
it's infinitely far away from the origin, but it's not. It's just another point in Minkowski space. I mean, why the whole construction seems tuned to singling out the neighborhood of one point. Neighborhood means finite distances from one point.
If you were to do a translation of that one, but maybe I can say a little bit more about that when I talk about translations. But if you were to translate these points, you're right that So if you do a finite translation of these points in the bulk, then you're right. This operator on the boundary would get multiplied by something. I think what you're speaking of is a translation by size rho itself, right? By the distance rho itself.
Yes.
So that's indeed something that would make the operator infinite. You're right. But it would make sense. I think the way one should think of is this: that there's some ball you have where some physics is happening, and you're out at infinity. And there's a sense in which it doesn't make sense to translate by a distance which is half of infinity.
I see. So, but then if the whole construction is tuned to singling out a point.
Singling out a point and a finite neighborhood of that point.
Yes, but there are other points which are equally good because all points in Minkowski space are the same.
So isn't that something one could say for ADS as well? Or ADS is homogeneous, but when you choose a boundary, you break that homogeneity, you pick some Hamiltonian, which gives you something. So the boundary of ADS is no different from the bulk of ADS.
I agree, but that happens, as you say, by picking out a Hamiltonian.
Yes.
Here, picking out a Hamiltonian will not do, right? You've broken translational invariance.
Indeed. So picking out a Hamiltonian is not enough, and you're right that you've broken the invariance that you have of Minkowski.
Let me say it again. I mean, you could set up a scattering experiment on your boundary where the scattering will not happen at the origin.
Where the
scattering will happen halfway between the origin and where you are. And that experiment would not then be described by.
No, you're right that this picks out some frame. So I think the way one should think about this is that there's a frame, there's some finite region of space in which physics is happening, and then one is trying to describe you take some region which is further out and you describe physics in that. And you're right that if you start making translations which are large compared to the radius of this ball that you're at, then that will not be well described by the original frame that you set up. But something else is troubling you, which I'm trying to understand. So the picture, at least that I have in mind, is that there's some region where you have something which is happening, which is some finite region. It's some distance of and you're out at some distance here. You have some observers here and here who are trying to describe this. And it doesn't matter so much, what they do, as long as, they don't try and, it doesn't matter so much if they make translations of size L, but you're right, they shouldn't try and make translations which are half of infinity.
Yeah, I'll just say what's bothering me. We should go on, but it's this. That suppose I try to set up a scattering experiment by hitting something at 4 points on the boundary.
Yes.
Where that scattering will happen is not up to you. It is determined dynamically. And that need not happen in a finite neighborhood of your origin. It could happen.
Can't you choose to use wave packets so that scattering happens in a finite region?
You could, yeah. But you could also do more general things. You can do more general things on the boundary that will not happen there.
Maybe it'll be, so maybe I'll say something a little bit which might make a little bit of that clear. Indeed, it's important that, when we do this, we use wave packets which focus us on points in the bulk, and that will indeed be important.
Okay, fine. Yeah.
There's a class of observables, and then in that class of observables, you smear them in such a way that that indeed the dynamics of whatever happens in the bulk.
Right. I'm just saying that more general things
observables are not good.
Yeah, I'm just saying that I think there are more general things you could do on the boundary that would not do this.
Indeed, and then correlators of these observables with those kinds of sources would not be well defined.
Yeah, exactly. Fine.
And we will see that happening.
Okay, fine.
We will see that happening.
Okay, thank you.
Just one comment. I mean, in ADS also there is a similar sort of discussion. But for example, if you set up a scattering experiment starting from the boundary and you don't focus the beams, then the point where the scattering happens can be, on a non-compact manifold. So it can be, infinite distance away from another point. Just to point out this, and then you can still analyze it.
No, but the difference here is that the renormalization of his operator depends on this statement.
Yes.
In ADS, that's not the case, right?
Yeah. Right.
I think I'll say this in another language, but indeed there's a subtlety here that does not arise in ADS. You're right. And in fact, let me. I'll come to it now.
Okay, then you come to it. But I didn't understand Shiraz's point. Just let me ask the question, then you go ahead. If everything happens I agree that Suvrat chose the origin as a preferred point. But if everything happens in some compact region in space and time, centered at the origin, so to say, then wouldn't it be okay that you go out to rho going to infinity and only this asymptotic behavior will matter, everything will drop out?
My understanding is it would be okay, but you could do something where you chose to make a scattering happen here or happen here. And if you did that, then these observables would not be very good observables. And you could choose to have wave packets which don't meet in this point in the origin, but which meet somewhere.
Sorry, Shiraz, just to understand your...
Am I breaking off?
It happens within some localized region. Isn't that good enough?
Within a finite region, a region that's held fixed as rho goes to infinity.
Oh, I'm not audible.
Can you hear me something?
Okay.
Yeah. So as Suvrat said,
okay.
If you tune your experiment so that the scattering happens within a finite region of the origin, meaning some region that's held fixed as rho goes to infinity, no problem. Okay. But if you just compute the correlation functions of 4 boundary operators at 4 arbitrary points, that will choose where the scattering happens.
Yes.
And that will not always be in this range.
Yeah.
So if you just choose 4 boundary points arbitrarily, I mean, you don't do anything perverse. You just choose 4 arbitrary boundary points. You will get a scattering experiment that in general will not be in this range. Because all you will have to do is basically solve a rubber band problem. You have 4 rubber bands coming from these points, and the sum of lengths of these rubber bands has to be minimized. And that will not in general be in this range.
Yes, this is correct, and I'll say it now in another language.
Okay.
This is
Thank you.
It's correct. Yeah. But this is kind of subtlety, but that by the way also happens in flat space. When you try and derive the LSZ formula and so on, you try and look at wave packets that scatter in some point in the bulk, and we have to do something here. You're right. This is more subtle than both the case of standard LSZ and of ADS, and I'll say this point right now.
Sorry, just one comment. So in ADS also, the thing that I was saying for massive case, you can have things, processes that occur kind of far away from each other in ADS compared to the ADS scale. In that case, you will not necessarily get infinity, but you will get something that cannot be quite, thought of as something that is happening in a small patch and hence happening in some flat space limit. So in that sense, this renormalization factor, I mean, the nature of things is the same, but it's just that this renormalization factor is giving you infinity rather than making.
I completely agree, but the issue is, whether these are well-defined operators.
Right. Yeah.
And these are not well-defined operators in general, only for very specific correlators, I think.
Yeah, they're not well-defined operators in general, but once you smear them correctly, then they do become well-defined operators.
Right, I agree with that.
Yeah. So let me say something about that. So
I have a question. Yes. Like, what happens if you have S channel and T channel scattering as well from the 4 points? That wouldn't be necessarily confined within a finite region, right? Because the intermediate propagator can be very large.
Yeah, it could be very large. So, maybe I can come back to this question sometime when I talk about the interacting theory. In fact, okay. we don't have something very sharp to say about some of these subtleties, but let me just tell you what we do have something to say about, and then you can ask more of these questions as we go.
Okay.
So, let's just take this limit and see what it gives us in terms of these modes. And, if you just take this limit, you will find the following expression. Okay, you will find something that looks like this. Okay. So if you just take this expression and just naively take its limit, you will find this following kind of expression. Now, this subtlety that Shiraz was discussing, or that we were discussing right now, has to do with the fact that these operators are somewhat singular, because you have this integral over nu, and this integral over nu, has this factor which grows exponentially with a factor of e to the pi nu over 2. Okay? And so this is what makes these operators somewhat singular. And now there are two ways in which you can deal with this singularity, and both of which physically have to do with this fact of trying to restrict the physics that happens to some region which is finite. And one of them is as follows. One is you consider observables, so you consider states which are in some sense bounded states, and so you consider observables of this kind. For example, there are other well-defined observables, okay, where the state psi has compact support in nu. Okay, or exponentially, falling off support. Doesn't have to be compact, it could be exponentially falling off. This is not a big, restriction in terms of states. In fact, this set of states is dense in the full Hilbert space. If you take the set of states and you say that, they have compact support in one of these modes, that's dense in the full Hilbert space. But it does restrict you to looking at states which have compact support. And for such states, if you look at observables of this kind, which correspond to looking at the expectation value of this observable in some state where you turned on a bulk source. Indeed, if you turn on a bulk source, you will naturally get objects where you have exponentially falling off support in nu. Then this kind of observable is well defined. On the other hand, if you start looking at correlators of these observables, so for instance, if you start looking at, yes.
I thought the issue was not the divergence in nu at infinity, but rather the divergence. At least the one that Shiraz was talking about was for rho going to z.
Yeah, these things are very closely related. This divergence in nu and the divergence in rho are very closely related for the following reason. I said I took this limit here. This limit is well defined, provided nu is smaller than rho, okay? Provided you don't take nu itself to be much larger than m rho. So if you have a process which receives contributions from very large nu, then this limit is a bad limit to take. Okay? This fact that there's some infrared issue which happens because some points go off to infinity. Those processes translate into processes which receive a contribution from large nu, and therefore they're not exponentially suppressed in this manner. You see the processes which are not exponentially suppressed in this manner are those where this field doesn't fall off as e to the minus m rho. So for instance, let's say you took a source and you pushed it halfway out to infinity, then the strength of the source would be falling off as e to the minus m rho by 2, not as e to the minus m rho. So in the language in which I'm describing, that would correspond to a source where, where you're receiving a large contribution from large nu. So these two things are related in this manner.
So I guess now I understand what Shiraz and you were saying. The important difference is when you broke up your Minkowski field into de Sitter, you had the masses going all the way to infinity, right?
Yes.
Yeah, I hadn't appreciated that. Okay, thank you. Now I begin to understand.
Exactly. Right. Now, so this is one way to look at things. But of course, if you look at correlators of this kind, in these correlators, are not well defined, because if you just look at the mode expansion corresponding to these correlators, this is something that receives, contributions from arbitrarily large nu. Okay? Now, there probably, this is some infrared effect that's happening, because, in these, you're looking at these 2 points, and, as you're discussing this you turn on sources at 2 points on the boundary, and, this scattering could happen anywhere. And so, this by itself is not well defined. Now, one way to cure this issue is to study Z of G, which is Z of X smeared with a function G of X. And if you expand this back in terms of...
Z is on the boundary?
G
or in the bulk?
Yes, Z is on. So Z is always a boundary operator. When I talk about a bulk operator, I'll use phi. And Z is always a boundary operator.
Maybe we've lost Suvrat.
Oh, sorry. Can't you hear me?
I can hear you.
Oh, sorry.
Can you hear me, Shiraz?
Oh, now I can hear you. Sorry, my speaker came out. Yeah, please.
Z is always on the boundary. So the notation Z is always on the boundary and X is always on the boundary. If I talk about a bulk field, I'll use phi.
Okay, thank you.
Z is always a boundary operator. So here I'm taking the boundary and I'm smearing it on de Sitter. This is a smearing function on de Sitter. So this is a DS smearing.
So smearing on the boundary. This is your focus.
Smearing on the boundary, yes.
This is you're going to focus these guys together.
Exactly. And if I do that, then if you expand this in modes, you will find that this looks like where this G nu L is just the integral of this function G of X with these modes. Now remember, I told you these modes were effectively like Fourier transforms. So if I choose some function, so that these modes, so these coefficients G nu L die off exponentially fast, you can kill this divergence, and then you would get an operator that is well defined. Okay? So if you use, G nu L to die off faster than e to the minus pi nu by 2, this is sufficient to kill this divergence that you have. So for instance, a simple setting to see this is, just the 2-point function.
Suvrat, just 1 minute. I'm sorry, I'm lost in all the coordinates. So the boundary is 3-dimensional, right?
Yes. So there's
tau and the 2 angles.
Exactly. And
okay.
Sometimes X as a shorthand for all 3 of them. Yes.
All 3. And then on the left-hand side there, you had nu and L.
Yes.
So you're doing some kind of integral transform on the tau direction, I guess?
Exactly. Tau direction and also the L direction. There's spherical harmonic in L in the sphere and it
okay. Yes. Okay. FRL already corresponds to one spherical.
Yeah, I wanted to call it nu, but nu looks like R, but yeah, it's F nu L.
Okay.
Phi L is a spherical harmonic and F nu L is a mode in the time direction.
In tau. Okay. Now I'm with you, and you're doing this transform, and if that falls fast enough in nu,
right,
then you'll be okay.
Then
all right, thank you.
So nu is conjugate to tau, roughly speaking.
Nu is conjugate to tau, exactly.
So falls fast in tau means delocalized. Falls fast in nu means delocalized in tau.
Correct. It's delocalized in tau. I mean, it doesn't have to be very delocalized. If you take a Gaussian in tau, that the Fourier transform falls off exponentially, falls off much faster than this. So it's not like it has to be completely delocalized. If you take a Gaussian, the Fourier transform is a Gaussian, and that falls off as fast.
Yeah, but it makes sense. You need to delocalize in order to focus.
You need to delocalize. Indeed, there is no such function of strictly compact support that has this property.
Right.
Every function that has this property has some non-compact support, but it doesn't. You could take a Gaussian.
It's like if we want to send a laser to the moon, we need to make it a certain size. Otherwise, we just go all over the place, right?
Yeah, right. Yeah, you could say that. Yeah, that's a good way to say it, right?
Yeah.
Exactly. Okay. So one example, might be just to, let's say you try to look at the 2-point function. Okay, so this 2-point function, does not converge, because in fact, what you will get will be if you compute this 2-point function, where this is what's called a Gegenbauer polynomial. Gegenbauer, how's it spelled? Gegenbauer. How do you spell it? Okay, whatever. Gegenbauer. Okay. This is some Gegenbauer function, and this Gegenbauer function you can write in terms of some exponentials, where this q is cos inverse of minus x1 dot x2. Okay. So indeed, in some cases where this q becomes, this integral would not converge if at large nu, when this q is real, and that is a sign of the divergence that I mentioned. And in the bulk, this is indeed a realization of the fact that if you compute this 2-point function x2, okay, this looks like k1 of mw by w, where w is square root of rho 1 squared plus rho 2 squared minus twice rho 1 rho 2 x1 dot x2. Now, if you try to take the limit that both rho 1 go to infinity and rho 2 goes to infinity, then this does not die off like e to the minus twice m rho. Okay? And so this is a sign of this sensitivity to this large nu behavior that I had. On the other hand, and therefore, this 2-point function as it stands as a pointwise 2-point function is not well defined. But on the other hand, if you compute after smearing, so if you compute this quantity, this is completely well defined. This is nice and well defined. Okay. So you need to smear these functions with the right kinds of smearing functions in order to get meaningful correlators on the boundary. Okay. So that indeed has to do with this infrared subtlety that we discussed at some length. Okay, so that's one point I wanted to make. Okay, are there any questions about that? I'll go on to some other points. Okay, now let me say some things about some results that we have. Okay, so
I have a question.
Yes.
Like why were z of x1, z of x2 undefined? I mean, not well defined. Exactly.
You see, let's say you thought of z of x1, x2 as, here's one way to see it. Okay, limit as rho tends to infinity and e to the twice m rho. And then there's some factors, polynomial factors of rho, but let's forget about that. You see, then you would get e to the twice m rho here, and there's one Bessel function, and this whole thing dies off like e to the minus m rho. So this whole thing diverges. So you get a rho divergence from the bulk. That's one way to see it. The other way to see it is that, if you looked at this expansion, you had this e to the pi nu by 2. And if I insert 2 of these operators without smearing with G nu L, I will get e to the pi nu times b nu and b nu dagger. And so I'll get something that just looks like, grows like e to the pi nu at large nu. And that's indeed what you see here as well. Okay. And that's why you need,
But b nu might have some dependence, right? B nu might have some dependence which might cancel.
This is a mode. So b nu dagger is 1 in the vacuum.
Yeah. You see, the only way it can be well defined is if the length between the 2 points is 2 rho, right? Because that it has to both have to go to the center and come back. Otherwise, you'll get infinity, because you've multiplied by such a large compensating factor that would be infinite unless this happens. So you have to have only those 2-point functions where they go through the origin, roughly speaking.
I was just wondering, for instance, for ADS, you don't have this sort of thing, right?
Yeah, for ADS, you don't have this
CFT, you don't.
Correct.
You don't. It's different.
Correct.
Why is it different?
Why is it different? It's a. I'm not sure there's a. I mean, this is in some sense some infrared effect. It's the fact that you have these massive fields and you have infinite volume at the boundary, and that's one way to think of it. But it's
even for ADS CFT, you have R4 at the boundary, right? Or S4, whatever.
No, you have S4 at the boundary, but things are naturally confined to the bulk once you pick some frame.
Yeah.
Which doesn't happen here.
If you solve a rubber band problem, you have 4 points in a boundary of ADS and you solve for the shortest rubber band thing, the place where they can meet has a finite ambiguity. Whereas here it can go all the way to the end.
No, here is considering 2-point functions, right?
Okay, I agree that you consider 2-point functions. It's similar. All the infinity. Yeah, sorry. I should stop.
Yeah, no, you're right. So something similar would happen for high-point function. I mean, yeah, indeed. So this is happening because, I mean, I think that's the correct way to understand it physically. In ADS, things tend to be. And one way to say it is, if you look at the distance between 2 points, there's no faster way to do this than here. If you look at 2 points on the boundary, sometimes they might be separated by distance which is less than 2 rho, which doesn't happen in ADS.
Yeah, exactly. If you move along the boundary, you get more or less the same distance as by going in the bulk. The difference is a finite.
Right.
No, I mean, the ADS safety dictionary tells you that finally, when you calculate both the bulk propagator and the boundary propagator, you should get the same answer. I mean, the calculation is the same.
Here also you'll get
That's
the
what
same.
ADS safety tells.
Some things are ill-defined. What we're trying to do is we're trying to define some dictionary of boundary observables, and this dictionary of boundary observables is not well defined unless you smear things correctly. I mean, unless you do something to focus them correctly, and
that's what I'm trying to understand. Why do you need to smear them? I mean, you don't need to smear them in ADS, so why do you need to smear them here? That's what I'm trying to understand. I mean, for the ADS safety correspondence, the boundary is also what boundary you are having right now, right?
Yeah, in ADS, if you take 2 points, phi of R1, phi of R2, you take the bulk point going off to infinity, that always dies off like 1 by R1 to the delta, 1 by R2 to the delta. This doesn't happen here, because the distance, may not, this 2-point function doesn't always die off like e to the minus 2m rho if you take 2 points. And similarly, if you take n points. I'm not sure if there's a much sharper answer that I have to why it's different.
Yeah, just to say that if you study rubber band, lengths of rubber bands, the difference becomes very clear. Right?
No, see, the propagators are not always given by lengths of rubber bands, right? So for instance, if you have for instance, a scalar propagator which is massive scalar propagator, okay, it's given by Bessel functions.
Right? I agree, but there's a path integral representation of that where the path.
Yeah, if you do the path integral representation, you finally end up with the Bessel function.
That's his
but the path integral is over lengths of rubber bands. The action for that path integral.
Yeah, true. But you're summing over all sorts of paths. That's what gives you the Bessel.
I agree, but all of these lengths have the same divergent behavior, and they differ in finite amounts. That is not true in flat space. That is a key difference.
Okay.
I didn't get that. Okay. Anyway.
Yeah, okay. I mean, it's just we can discuss how to understand more intuitively, but if you just look at the expression, it's absolutely clear, right? Here's the 2-point function, and this 2-point function, if you take the limit as you multiply it with 2m rho, which is what you should do to take both points to infinity, you find this diverges. You'll either get 0 or infinity unless x1 dot x2 is exactly of the right kind, unless it's exactly minus 2. And you see that also on the boundary. You take these modes, you multiply it, you'll get something that diverges, that blows up like e to the nu cube. And it's true that if you smear it, you will get something that's well defined. You can compute what that is. So that at least in this language, in the equations, it should be clear.
Sir, isn't the point somehow that the holographic renormalization is local, it's attached to legs? So you can make finite quantities even if you are able to renormalize individual. It's not like it depends on any point in the bulk or anything like that.
In ADS, you're saying?
Yeah, that's what lets you compute finite.
Maybe. I mean, I think it's very interesting to understand some of these subtleties in detail, and indeed, this is a subtlety that we have some understanding of, but don't have a very good understanding of. Maybe there's some way to understand it in that language. It would be great to understand it in that language. Okay.
Hey, I'm very sorry, Suvrat. Just many slides back when you wrote the Laplacian in terms of the 3D de Sitter Laplacian, and you got this infinite tower of masses. Can you just once remind me how exactly that happened? Those news which appeared,
yes,
I think it's one slide before, right? Where is it? Ah, yeah. I think it's some, yeah. So the box minus m square in Minkowski, I think becomes this de Sitter minus 1 plus whatever this new gamma symbol of yours is.
Yes.
And then you have a sum of gamma from 0 to infinity.
Exactly.
That is the statement.
Exactly.
Okay.
And then you strip off this part. So you strip off this part, and you just get the integral over this field.
Right. Okay. Thank you.
Fine. Okay, good. So now let me say a few things about, that we understand from boundary to bulk. Of course, in ADS we have the HKLL reconstruction, which allows you to go from, which basically tells you that, if you do an integral on boundary time, then, what HKLL tells you is, you do an integral in some way on the boundary, and that lets you represent some point in the bulk here. There's something similar you could do, we can do here. And that arises just from the following fact, from the fact that, all these modes that we have, you can get them by integrating with a suitable smearing function. The suitable smearing function is basically just a function that is, these modes that I discussed were orthogonal modes or orthonormal modes. And if I just pick out, the function that picks out the new L mode, then that will just pick out this oscillator that I was calling B tilde. And once you can construct the oscillator, at least in the free field case, you can construct the whole free field, which is basically what HKLL does in the bulk. In some cases, we can do this more explicitly and write down a nicer, more explicit expression. For instance, here is one example. Okay, so let me take this operator and let me integrate it over the sphere. So these are these are bulk coordinates. Except that I've kept track of a rho naught and a tau naught coordinate, and I've integrated over the sphere in the bulk. Okay, this is it's an S wave, and this is just to make, so I can write down a nice formula, and this turns out, to be the boundary S wave, but integrated with the following kernel in tau. Okay, so this is a formula which is it's a nice formula, and it tells you that you take the boundary and you integrate it in this way, and that gives you the bulk. Okay, so this is like a boundary to bulk transfer function. It's like the function that HKLL wrote down, except that I've made life slightly simpler for myself by doing the S wave. For the other cases where you integrate with non-trivial harmonics, we don't have a nice closed form formula of the same kind. But in this case, we have a nice closed form formula that tells you, here is the kernel that you need to integrate with on the boundary so as to recover the bulk at some point rho naught.
So this is the classical question you have to solve is, given the boundary values,
yes, what
is the bulk value? Right?
Exactly.
It's like solving the Laplace, exactly. The Green's function. Basically.
Exactly.
Okay, and HKLL had many different ways of producing the same field. Do you have some analog of that?
That might, yeah, it's a good point.
What is this many different ways, Shiraz?
If you take ADS, you can produce, so if you take ADS, you can produce a field by looking at this, thing, or by looking at, any causal wedge that captures this point, you can use. So you could use this, or you could use this. So you could,
just whatever Rindler wedge covers.
Yeah, you could use this one, or you could use this one. Yeah, that has to do with the following, and perhaps there's something similar one can do here. This ambiguity in ADS has to do with the fact that space-like modes in ADS don't propagate, and that's also true in flat space. So perhaps it's possible to take this mode and rewrite it in a different way using part of the boundary. We haven't thought about that more. That's a good question, but I don't know the answer immediately to that. It might be possible to rewrite this using something more compact than this. This is one representation, and maybe there are alternate representations.
So this integral supported over the entire de Sitter? This integral supported over the entire de Sitter.
Yeah. But that's what happens in HKLL as well. The integral is supported over the full light crossing time of HKLL of ADS.
Sorry, just in this causal diamond, right, that you are carving out?
Okay, you're right. But the simplest version of HKLL that you do just takes the full light crossing time of ADS and writes something in this way. That's the analog of the formula that I have, right? You take the full light crossing time, you do some integral on the boundary, and you get some point in the bulk. Now you're right that if you move the point here, then you can write an integral over a smaller diamond.
That's how you can get these multiple things that
Yeah, and that's how you could get these multiple things. And perhaps we could refine this formula to write something in terms of a smaller diamond. And that's a good question. I don't know the answer immediately. It's possible that we could refine this to write something in terms of a smaller, not over. Yeah, of course, what we are looking at here is something slightly funny. We are looking at what an ADS would be the analog of an S wave. So it would be like an integral over the sphere. And then probably we would need to use, even in ADS, the full kernel, which goes over the full light crossing time. But you could ask, what if we didn't do the integral, but we only looked at this point? Could you do something in a shorter interval? Perhaps you could. Okay.
Maybe if you take a bunch of Rindler observers, spherically symmetric, which all have the same turning radius as measured from the origin.
Yeah, if you take spherically symmetric, it's possible we can't do much better than this. Even in ADS, you might not be able to do much better. This ambiguity arises from the fact that in ADS, a single point is part of many different causal wedges. And if you take a circle or a sphere in ADS, then you might need to use all of ADS. I meant, maybe I'm wrong, but I meant instead of making the Rindler guy turn right at the origin, you could have them turn some distance away, construct a family like that. Okay. I don't know. You basically have a bunch of accelerated observers, right? One way to think of these set of observers, indeed, is to think of them as some spherical Rindler observers. I mean, some observers.
So if you cut out a hole and make them turn before you get to the origin, okay, maybe I'm wrong.
Yeah, so you're saying that you could think of other frames in which you could do this, perhaps. You could,
Anyway, I don't have it very sure.
I mean, there's a lot to say here. That we have a lot of ADS CFT literature, and there are many very interesting questions. But this is basically just entirely new. So there are a lot of these very interesting questions that we don't have an answer to.
So I have a question regarding HKLL. So for HKLL, is the understanding that, so for instance, for Z, you would have, say, trace F square, and on the left-hand side, you would have the dilaton. Is that right? 5 would be the dilaton.
Yes. Right? Yes, for instance, yes.
Yeah, so that would mean that F square would have a non-trivial correlation with phi, right? I mean, it would interact with phi in some. I mean, if phi, phi in ADS CFT is just the source for the F square. It can't have correlation functions with F square, right?
No, that's not correct. So so this is maybe a longer discussion, but in the bulk, the idea is that if you take the bulk operator and you take it off to infinity, that turns into the boundary operator. So let's forget about ADS CFT. Let's just say there is you take the bulk operator, you push it to infinity, you get a boundary operator. In terms of that boundary operator, you can reconstruct the bulk operator if I give you that boundary operator for some amount of time. Just think about the boundary value of the bulk operator. Think of the bulk field itself. And
but the boundary value of the bulk field is like a source for the Z. It's not. It can't be Z. It's like a source for the Z. That's what ADS CFT tells you.
Integrating over time, right? If I give you the boundary value over some amount of time, then I can reconstruct. You're just solving the partial differential equation inwards. So if I tell you the boundary value over this full time, then I can use it to get what's happening in the bulk.
No. I'm not talking about that. I'm saying that let's talk about ADS F square. Okay. And then phi would be some, if phi is some bulk operator, then phi would be some dilaton, right?
Yeah, let's just think of a scalar field in ADS. I mean, this formula is just, the analog of this formula in ADS is just manifestly true, that you take a field which satisfies the free equation of motion, you can write the field in the middle in terms of its boundary values for the integrated over length of time.
That's what I'm disputing. I mean, it can't be written that way. That's what I'm disputing.
This is just a property of partial differential equations.
It's not a property of partial differential equations.
Sorry, maybe we can move some of the discussions to towards the end of the talk.
Okay. Maybe we can discuss more. Maybe I'm not understanding your question, but okay.
Suvrat, one quick question.
Yeah.
Even for the S wave, you could have restricted your support over some light crossing time, as you said, right?
We could have restricted our support for the S wave over. You're right. You're saying even in the S wave, I could have restricted my support not to full ADS, but something like this.
Yeah, that's what I mean.
Maybe, except notice that this wave talks to this for a longer time. So, what you're assuming is that you write this wave in terms of this, and maybe that works. No, you're right. Even for the S wave, you're right. You could do it. You could have done it for the S wave, and in fact, we've written a formula ourselves of this kind. I remember. Yeah, indeed. So you could take a band here, and you could write something in this in terms of a band in a shorter time. Indeed, you do. And we have ourselves written a formula of this kind. Yes.
Thank you.
Yes. So we did this. You could do it. You're right. And maybe you can do something here. Maybe you can restrict the support of tau. It's an interesting question. As I said, there are many very interesting questions here, which we've not.
Yeah, that's what I meant in terms of tau. You could have.
Yes, you could restrict the support of tau. You're absolutely right. You could do that. Yes. Okay.
See, bulk descriptions and boundary descriptions are two complementary descriptions, right? You can't express boundary operators or bulk operators in terms of boundary operators or boundary operators in terms of bulk operators. They're complementary descriptions, right?
So here, we're just talking about the boundary. There's no boundary theory. There's no independent boundary theory. We're just talking about the boundary limits of bulk operators. There's a partial differential equation that relates the behavior of the bulk operator at the boundary to the bulk operator in the bulk. I mean, that's just a property of partial differential equations. If you give me the boundary values of some solution, I can determine what its bulk values are.
So it's not like ADS-CFT, you're saying?
In ADS-CFT,
in that
it's
sense,
exactly the same thing, but let's.
No, in ADS-CFT, that's what I'm disputing. If it's like ADS-CFT, then it's not correct.
Okay, maybe let's leave the philosophical discussion aside. Here we have the boundary.
It's not philosophical. Why is it philosophical?
Because we have the boundary value of a bulk operator, and I'm trying to.
Yeah, the boundary. So for instance, if you take the boundary theory, okay, you have a trace. So suppose you have the Engels theory. Okay, so you have some phi on the boundary multiplied with trace f square, correct?
Could you?
That acts like the source for the trace f square. Now that phi has a certain bulk counterpart, which is the phi that you have here, and the z is like the f square.
Yeah.
But as we all very well know, the j and the phi in a scalar field theory don't have correlations with each other. Correct?
Okay, so this is a question of the extrapolate dictionary in ADS-CFT, which is something which is beyond the scope of this talk. It's the point that it's true that if you look at the non-normalizable part of the bulk field, that you should think of as a source. But it's also true that if you look at the normalizable term in the bulk field, that turns into the boundary operator. Sandeep and so on worked this out in the early days of ADS-CFT, but maybe we could have that discussion separately. Here, we are just talking about partial differential equations. That is a bulk field. There are its boundary values, and we are trying to reconstruct the bulk in terms of the value on the boundary.
If it's like Dirichlet boundary conditions and so on and so forth, I understand. I mean, if it's like electrostatics, I understand. But if it's like ADS-CFT, then it's not the same thing.
Okay, let's just talk about partial differential equations here.
If it's like electrostatics and partial differential equation, then I understand. Then if you have a boundary theory and you have boundary values, like you always express bulk things in terms of boundary values.
Fine, so
that's correct.
It's not electrostatics; it's a dynamical thing because you're integrating over time.
Yeah, it's a dynamical. So even if you have electrodynamics, it would be the same thing.
Yes,
it's
so
just Green's functions,
exactly.
Normal Green's functions.
That's all this is.
Yeah, so it's not HKLL. HKLL is different.
Okay, I think HKL is the same, but perhaps we could move the discussion to offline, and we can. Okay. Yeah. Okay, thank you. Yeah. Okay, so this is one formula. Now let me say one more thing about causality. Okay. So if you look at this formula, you'll notice something interesting, which is that let's say you put tau naught equal to 0. This is something which dies off exponentially fast in tau. Okay, so it dies off like m rho naught times cos tau. In fact, there's a general result one can show about causality, which is if one takes integral z of tau gamma, g of tau gamma, tau omega, where this g of tau omega has the property that it dies off like e to the minus delta cos tau at large tau. Then this commutes with all bulk operators. on the tau naught equal to 0 slice, so the bulk tau naught equal to 0 slice with rho naught smaller than delta over 2m. Okay. So if you take a smearing function that dies off very rapidly, that smearing function corresponds to bulk operators which are in the exterior of a large ball in the bulk. So the picture one should think of that goes along with this is that we have this boundary, and if you think of some smearing function which dies off very rapidly in the bulk, then this, oh, I didn't draw that well. Okay. Anyway, if one thinks of a smearing function that dies off very rapidly, then this corresponds to something which is in the exterior of a large ball. Okay, so in the bulk. So this is my boundary. This is my bulk. Okay. And the fact that this operator, which dies off exponentially or doubly exponentially fast, commutes with everything for this rho naught smaller than delta by 2m, means it is localized in the region rho naught larger than delta by 2m. So this is the tau equal to 0 slice, and this operator is localized in this region. It's in the exterior of a large ball. Okay. So this is the sense in which you can look at operators which are in the exterior of a large ball, thereby looking at smearing functions of this kind.
Yeah. Can I understand this intuitively as follows?
Yes.
We're smearing only over a small time.
Yes.
And so the signal cannot reach too far.
That's one way, exactly one way to understand it. Right?
Okay.
Right. Exactly. Okay, good. Now, let me say something.
And sorry, Shiraz, this is small tau time, right?
Small tau time, which
yes.
is small time on de Sitter. It's a small interval on de Sitter.
Yeah, on de Sitter. On de Sitter. Not, I mean, just not Minkowski at any rate. But
no, it's not with small Minkowski time, small de Sitter time. It's right.
Okay.
Okay. Let me now say something about the interacting theory. Okay. So our understanding of the interacting theory is limited. Partly the reason it's limited is because it's hard to do explicit computations. But let me say something about the interacting theory, which suggests that at least, we believe that the same extrapolate dictionary should make sense even in the interacting theory. The idea is that, let's say you have some correlation function with some insertion of this and some insertion of some other operators. And I want to take the limit as rho tends to infinity of this with this factor d rho, which has this exponential of m rho part. Why would I believe that this limit continues to exist in the interacting theory? The point is that in the interacting theory, the general rule for computing such a correlation function is that you look at this point, which is phi of rho x, and it's connected by a propagator to some Feynman diagram that depends on the other insertions. So that is the general rule for computing this kind of correlation function in perturbation theory. So again, I'm assuming that I have some perturbative way of computing this correlator. So when I say interacting theory, this is still within QFT. I don't have gravity, and actually in perturbative QFT. Then the general rule is that you would compute it this way. And so the general expression you would expect is that, let's call this rho tilde x tilde, this is the internal point, is that you would get some propagator that would connect, this point to something which is then integrated over this internal point. Okay? Now, from very general arguments, we expect that this propagator in the interacting theory has some Callan-Lehman spectral representation. So we can write it with some weight ds, where this is the propagator that corresponds to a field of mass s. And if we assume, and this is what we need to do also when we define an S matrix, that this weight function has support which looks like delta of S minus M plus something. And if we assume that mu of S is equal to 0 for S smaller than M, then you see this propagator, the fastest fall off that it has is indeed e to the twice m rho. Okay? All of these propagators have a fall off which is controlled by S, okay, which in fact is e to the minus S rho. This propagator falls off as e to the minus S rho at large rho. But in the spectral representation, if you assume there's a delta function at S equal to M, and moreover that there is no support for s smaller than n, then indeed this whole propagator has some fall off which looks like e to the m rho. So that suggests that even in the interacting theory, this limit is well defined. That being said, there are some additional subtleties that have to do with the infrared divergences that we discussed earlier, which have to do with, with what is the precise kind of smearing one would need in the interacting theory in order to ensure that these correlators are well defined. We don't have a very good handle on that because we don't have explicit computations, but it seems reasonable that, if you again, choose wave packets so that the scattering and all the dynamics happens in some finite region in the bulk, then, this infrared divergence should not occur either. So that combined with this argument suggests that this extrapolate dictionary should make sense in the interacting theory as well.
Yeah. Sorry, Suvrat, I'm not seeing what you just said is adding to this argument about this e to the s rho and so on, because the caveat is still there. I mean, so what exactly does this argument help you with? This delta?
Well, this tells you, for instance, that the particle that you're looking at has to be a stable massive particle. Otherwise, it just doesn't make any sense. So, this is the kind of argument that one makes also in LSZ, that, the spectral representation, you look at this, the form factor that has to have a delta function at the right point. So if you didn't have a delta function, and you didn't have, a stable massive particle, then this is not something that would make sense.
Okay.
So the renormalized mass must appear, and this mu of s has, should have a delta function at that renormalized mass.
Right. But that, okay, fine. But this is not necessarily saying that all the process should happen in finite distance around origin, right?
This by itself is not saying all the processes should have at a finite distance. That's something that you need to ensure by taking the right kinds of wave packets.
Right.
So that's also what we say in LSZ, that we construct wave packets so that the processes happen at some point in the bulk, and we need to construct wave packets here as well so that the processes happen at some point in the bulk. We don't have a complete characterization of the kinds of wave packets that you need. In the free theory, I said the kinds of wave packets you need, there's a very simple condition you need to put in them. Here, the kinds of wave packets you need are intuitively those that cause the scattering to happen at some point in the bulk. But we don't have a complete characterization of those wave packets, but we think they should exist.
But I mean, previously this discussion that you had about the support on the new spectrum, was that the smearing that you need is somehow kind of delocalized in the new, right?
Yeah, it might be a little bit more than that in this case. Just having that smearing might not be sufficient in the interacting case to ensure that all the new divergences go away.
No, but even if you take that, then I mean, even if you take this kind of more basic condition that you want it to be delocalized in the new,
yes,
you just discussed a situation where if you have, that was the tau space, right? I mean that.
Yes.
Finite.
So
the smearing. Let me ask this. So do you expect the smearing to be delocalized in the tau space or kind of localized?
That is necessary even from the free theory that it's delocalized in tau space. It can be sharply peaked in tau space, but must always be delocalized in tau space.
But then it should have some things which lie outside the ball, as you said, right?
Which lie? No. So the question of whether it's in the ball or not has to do with the fall off at large tau. You see, this is delocalized in that it goes up to tau equal to infinity. It's a question of what the fall off at large tau is. So if the fall off at large tau is rapid enough, then it is localized in the bulk at something which is larger than this. This actually follows from microcausality. It would also be true in the interacting theory as an exact statement.
Okay.
The fall off at large tau gives you a localization in the bulk.
I was just wondering if things are working against each other, not working together.
Why? In that, if you take something which falls off at large enough tau in rapidly enough, then that localizes you to some region outside the bulk. Why is that working against?
But here on the next slide, you wanted things to be in the bulk.
You wanted things to be in the bulk. Oh, you're right. So just putting the fall off in tau is not enough to make things in the bulk. By the way, so putting things in the bulk is somehow has to do with the fall off in the other space, which is the new space. In the free theory. So in the free theory, ensuring a certain fall off in the bulk had to do with this e to the minus pi nu by 2. It had to do with fall off in the Fourier domain. It had to do with this property. And you can ensure both properties. I mean, you can ensure that it has this fall off in nu space and it has cos tau fall off in tau space.
Okay.
So there are smearing functions. I mean, this smearing function is one of this kind. It has the right fall off in, if you Fourier transform this, it does have the right e to the minus pi nu by 2 fall off in nu space.
So, but you don't sorry, you don't want this fall off in the tau space, right?
Why? I mean, saying that it has this fall off, it just tells you it commutes with something, but it could be somewhere here, right? It could be localized here. Like for instance, let me take this example. This is a nice operator for me, right? It has this fall off in tau space, and it's localized at some finite point, which is rho naught. I just don't want the point to go off to infinity.
Okay.
So this operator, for instance, does have this fall off in tau space, and it's localized at a nice bulk point, and I'm very happy with that operator.
Okay. Thank you.
Suvrat, this one quick suggestion. I mean, intuitively, it would seem the following: that if your wave packets are localized in the bulk faster than e to the power some number times mass times distance, then you will have no infrared issues, where that number will be or some order 1 number.
If they were localized in the bulk in that way, yes, that sounds right. Yes.
Because the danger is that you pick up exponentials in distance.
Yes.
So if you pay a price that is that's pick up exponentials in mass times distance.
Yes, correct.
So if you pay a price larger than that, you're probably fine. So for instance, if it decays like a Gaussian, you're almost certainly fine.
That's correct. Yes, that is correct. That's the intuitive reason why we believe this should continue to make sense in the interacting theory. But to prove it formally is something that we found hard.
Hey, I'm sorry we have had so much discussion and I'm still confused about the free field case. I'll just ask the question, but I think then, for slow people like me, we'll have one remedial session with you, Suvrat. But the thing I haven't understood is this. See, in ADS space, I always thought the Bessel functions physically, which had therefore a tail going out to infinity, was because you are in a box. Now here we are in flat space. And what I have not understood is if I can certainly construct a wave packet for whatever massive particle you want, which has strictly got compact support. Isn't it? In Minkowski space.
Yes.
We all agree.
Yes.
How can you possibly image that on the boundary?
How can you possibly image that on the boundary?
Yes.
The reason you're imaging it is because in this case is because your boundary is going all the way here, right? So that's how you're imaging it. Because your boundary is not, it's this point. So it covers all of this region somehow. That's how you see it. At any row slice, it covers something like this.
No,
so
but I see. Sorry. Isn't your boundary, formally speaking, at rho going to infinity?
It is at rho going to infinity, but if you take the limit in the right way, at every row, you see that this wave packet is there, and therefore, if you take a smearing function which has some behavior in tau, you can take a limit as rho goes to infinity. But really, you should think of this boundary as doing something like this.
So maybe this is what I haven't understood. Then please go on. But can't you construct a wave packet which has support only up till rho equal to rho naught, some finite value, and vanishes outside?
Yes, you can.
Right now, I try to do your limiting procedure. So for every rho greater than rho naught, I have no image, strictly no image.
You have no image, but remember it goes. You see, this is the same question you could have asked about HKLL, which is you have some finite thing here. How do you image it from the boundary? The way you image it is by using later time, right? You use light rays that reach here, and that's how you image this guy. This is just QFT. So you use light rays that reach out, and then you image it. So that's what I'm doing here. You're saying you had something here, but I'm trying to reconstruct it from here, and I can.
You can. You send out images. Rays.
Yeah, because I have a boundary of the entire. Somehow, we would like to say, although we're not close, that this is where the dual of flat space should live. So it looks like, some boundary of flat space.
No, sorry, where does it can't be then just at, I see it's that blow up with the tau coordinate put in.
Yeah, exactly.
Okay.
Right. It's a subtle thing, and you're right, it's confusing that
I see. Okay. Thank you. Go ahead. Sorry to everyone. Yeah, go ahead.
Okay, good. So let me just say a few things about what we can say about holography, subject to these caveats about the interacting theory. So let me just take 5-10 minutes more. I know we are well over time, so I'll stop soon. Okay. So let me just say what we can say about holography of information. The statement is, the conjecture would be that, and this is subject to these assumptions that this, the limit makes sense. is that we look at a subalgebra of operators. This is algebra of operators smeared with functions die off as e to the minus delta cos tau. Okay, you take this algebra and you take this algebra of operators at I plus minus, okay, which is operators on I plus in the range minus infinity to minus, I mean, this is the algebra that we had earlier, okay, and that this algebra, so let's call this algebra A infinity, okay. So the claim is that A infinity, okay, has all information about the bulk. In a gravitational theory. Okay. So let me just explain why this is somewhat surprising. I mean, it's what we discussed also at the beginning of the talk. You know, this is the set of operators that you should think of as being outside a large ball, okay, which is controlled by this fall off delta. Okay, so remember I said that, you know, operators which fall off rapidly enough, maybe I should write 1 over delta.
Sorry, but this ball is of finite size, right?
This ball is of finite size, yes. So these are operators which are outside a ball which is of size, you know, now I made it 1 over delta. And these are operators which are outside. I mean, this is the same here. You know, these operators are things which miss an interior which depends on this 1 over epsilon. Okay, they miss a ball which is of radius 1 over epsilon, and these miss a ball which is of radius 1 over delta. So both of these operators in a QFT would be missing a large ball in the bulk.
Well, sorry, this is what I'm saying. I mean, from this point of view, you want the ball to be large, but from the other point of view, you want the ball to be small.
No, I want the ball to be large, but I just in the other point of view, I just don't want the ball to be infinity. I don't care if it's large or small compared to rho, and there's a rho goes to infinity limit. And, you know, I'm happy to take a ball which is large compared to the mass or compared to, you know, 1 over the mass. But I just don't want the interaction to go off to infinity. The only thing I need to worry about in my infrared effects is the interaction shouldn't go off to infinity. I'm happy to consider operators which are, you know, which are far out compared to m. There's an order of limits there.
But here in this massless case, you have epsilon going to 0 limit.
No, I'll never take epsilon going to 0. I'll always keep epsilon to be finite and delta also to be finite.
Okay.
In this, at the result, the claim would be that this would work for any finite value of delta and any finite value of epsilon.
So, but then this would describe processes that are not happening in that finite ball. Is that correct?
No. So this, yeah. So this in QFT is the set of operators which are outside a large ball. Okay. So these are operators in this white region that I marked in a QFT.
Yeah.
And they would miss information in QFT about things that are happening in the interior.
Yeah.
Now the claim is in gravity, they would not miss information. They would also have information about this orange region.
I see.
Okay. So in a QFT, they would miss information about the orange region, and the claim would be, but the conjecture would be, it's a conjecture because, you know, it's subject to the fact that this whole story makes sense. And maybe it doesn't make sense for some reason, for these infrared issues are too severe or something. But, you know, the conjecture would be that, you know, if the story makes sense, then in theory of gravity, they would also have information about the orange region.
So this is a new statement, right? Now that you have this.
Yes, this is a new statement gravity. I'm now making. Yeah.
Which
so I won't go through the whole proof, but let me just quickly explain how this works. Okay. So the main thing is that, you know, if you look at this set of operators, is to prove some analog of the Richt-Leader theorem. Now it is to prove, if you look at the set of operators which I called A hat, which are operators which are smeared with the, you know, rapidly dying off functions, and you look at the set of operators here, then the action of A on the vacuum, okay, is dense in the Hilbert space. You shouldn't be so surprised by this. This is a statement which is also true in QFT. It's a statement that if I look at operators in the complement of a large ball, which is what I was looking at, then the action of operators in the complement of a large ball is dense in the Hilbert space, even if I miss the orange region. Okay? So it's true, I can always, by acting with an operator algebra from some region, generate all states in the Hilbert space. That's not in violation of causality. That's a QFT statement. In fact, this statement one can prove in the free field theory, it's a true statement. Okay. And then, I mean, this is the same argument that in fact we had previously, but just enhanced with this new algebra and this new Riech-Leader theorem, which now works on this boundary. It tells you that if you look on the boundary at smearing functions with a certain fall-off, they have sufficient entanglement with other operators on this boundary at I0. Okay. If this is true, then you see that if you take any operator, let's say you want an operator that creates a transition from the state n to m. You can write this operator as an acting on 0, 0, am dagger, okay, where these are the operators that create this. But the key point in gravity is that this projector on the vacuum is also an element of this algebra that I was calling A infinity. This projector on the vacuum, in fact, lives on the past boundary of future null infinity. You can also locate it on spatial infinity, but it also lives on the past boundary of future null infinity. Okay. And therefore, because these operators live, in this algebra, this operator lives in this algebra. Therefore, this whole thing lives in this algebra. And so the statement that we need, I mean, this argument is just the old argument that we had earlier. The fact that once you have the projector on the vacuum and you have a Riech-Leader property, that's sufficient to argue for this kind of holography. Okay. I'm well over time, but let me just give you one example, since this argument might have seemed a little formal. Okay, this is related to what we said at the beginning, and then I'll stop. Let's imagine that I took this state. This is the example that I was giving earlier for a news operator. Let's say I took this state, which is a state of a massive field smeared with some function f of x on the t equal to 0 slice. So these are now Minkowski coordinates. Okay? And I say, so I'm making two simplifications here. One is we know the form of the state psi, which is it's of this form. And second is we can work perturbatively in lambda. Then someone could say, how can you determine this state psi by making observations at infinity? And once again, the point is, you measure the Hamiltonian and you measure one of these operators at infinity. In fact, in this particular state, it turns out you can just measure, an insertion of a point, because this state is a bulk state. It's some nice bulk state. So you can take this function f to have compact support. And if you measure this correlator, a simple calculation will show that it turns out to be this. X dot x f of x. And this object you see is the three-dimensional Laplace transform of the function f of x. And if I know this right-hand side for even an open set x on de Sitter 3, that is sufficient for me to completely reconstruct all the moments of f of x. Okay. And so this is an example of how it is that in gravity, even though you're acting with a unitary operator that has compact support in the bulk, you're able to detect it from the boundary. And of course, once again, the magic is not done by any of the QFT story. It's done by the insertion of the Hamiltonian that doesn't commute with this. And that pulls down the relevant operator so that you can measuring once again correlators of the energy and other observables gives you something that you can use to determine the form of the bulk state. This is of course a very simple example of a state. I simplified life for myself by constructing this perturbative state, but the general argument is that this would work in general. Okay, so let me stop here. I went way over time. Let me just conclude with the punchline. The general model. The general story is that we want some new formalism for describing massive fields in Minkowski space at infinity. The conventional formalism is to describe massive fields at I plus or I minus, and that's not so good from the point of view of holography. And therefore, we propose that it might make sense to consider the blow up of spatial infinity and consider this new limit of massive fields at the blow up of spatial infinity. And it looks like this blow up gives us some nice properties. If we smear these operators at spatial infinity correctly, we get some sensible correlation functions. There's some nice bulk to boundary map like HKLL. There's some nice Riech-Leader theorem that one can show. And there are some arguments to suggest that this continues to make sense in the presence of interactions. But this limit is indeed a subtle limit, as we discussed. And maybe there's some reason why the whole thing doesn't make any sense. but we think it's something very interesting and worth exploring. Okay, so let me stop here, and sorry for going over time. I'll stop here. Thank you.
Let's thank Suvrat for a very nice talk. Questions?
I'm wondering if we can have I got to run, but I'm wondering if we can have Suvrat back for a Q&A some other day. Suvrat, I don't know.
I'll be happy. Yeah, of course, yeah.
Anyway, but thank you very much. I'm really sorry, everyone. I just have out of time. Sorry. Thank you.
Thanks. Yes. Thank you for all staying so long. Yeah.
Suvrat, to me, everything you said sounds completely reasonable. But I was just wondering whether one could do more. That is, not restrict to this class of observables, and try to find the dual of all of Minkowski space, not just a finite neighborhood of a point. That more will have more features that are less familiar. The operators the renormalization will be different and so on. Yeah. But I was just wondering if one could increase the ambition.
Yeah, maybe. I mean, that would be great if we could do that. It would be great. I mean, this is just a very new formalism, and so even here we are not completely sure that all of this makes sense when you turn on interactions and so on. And maybe there's a way to just to do something which makes sense even if you're away from the finite.
But your main worry is that this renormalization doesn't work.
Exactly.
That's the main worry. Yes. Right. And of course, if you go dynamically, of course, you would have to do some sort of dynamical renormalization.
Yeah. So we thought of a lot of possibilities. We thought of if one could go to null infinity and do some renormalization there and get some operators at null infinity. So we thought of a lot of possibilities, and indeed this is one that we found that seems to work partially, but maybe there's a cleverer way of doing the renormalization. For instance, rather than taking the limit, you smear over the radial direction and then you go to infinity or something like that. And maybe there are clever ideas one can have which would do better than what we have.
One more question along these lines. This worry of exponential divergences is largely a worry of Euclidean space, right? Oh no, but you say even in Minkowski space because you're going to spatial infinity. I see. It wouldn't be there if you went to time-like infinity because that would just be a phase.
Yeah, then it wouldn't be there, exactly.
I see. So the worry persists in Minkowski space because you're going to spatial infinity.
Exactly.
If you were just capping off like this, yes, everything would be pretty straightforward.
And that's the standard description of massive particles, isn't it? To go to time-like infinity.
Okay, thank you. Yes.
Yeah. There might be a nice Euclidean version of the story, which is roughly goes along the lines of you do Euclidean continuation, so of de Sitter time, and then you have this boundary which is which is just some S3, and now you specify some. So it would be like the version of Euclidean ADSCF. You specify some boundary conditions on that boundary, and then you say that you look at the bulk action subject to those boundary conditions, and that gives you something on this boundary S3. So there's some theory that lives on this S3, which is not DS3 but the S3, and that computes this.
But this Euclidean version will have your problem.
It will have the same problem of U to the envelope. Yeah. I mean, same problem, or maybe you can deal with it by doing the smearing. Maybe a fancier way to say it is that these are operator valued distributions where the class of test functions is not all functions, but functions which focus in a particular way.
Or maybe just the rules of renormalization are different, like they're process dependent.
Yeah, okay, maybe. Yeah.
I mean, that would be very new, I know, but somehow more adventurous.
Yeah, okay, maybe, yeah.
Okay, if there are no further questions, let's thank the speaker again.
Okay, thank you all for listening. Thank you.
Great talk, Suvrat. Thank you.
Thank you very much. Yeah, thanks for your comments. Okay.
Thank you.
Okay, see you then.